Okay, thank you for the nice introduction. Today I want to present you our Nextflow pipeline for network-based disease module identification and drug repurposing. But before we talk about the pipeline, let's quickly talk about the background. What are disease modules and what do we gain from identifying them? Disease modules aim to capture the molecular mechanism of the disease. And this is necessary because most disease-associated or causing proteins do not act in isolation. Huntington's disease, for example, is a neurodegenerative disorder caused by a mutation in a single gene called huntingtin. This results then in a mutant protein. This sounds simple enough, but this mutant protein actually interferes with a range of cellular processes, including transcription, proteolysis, or mitochondrial function. And this overview on the right still only shows a fraction of the processes which are currently involved or known or assumed to be involved in the disease. But despite all those puzzle pieces, we still don't understand the full details of the exact mechanism, and this is the case for most complex disorders. This is a problem because understanding the mechanism can be crucial to identify novel therapeutic targets and guiding treatment research. And this is now where disease module inference comes in. A typical approach starts with a set of disease-associated genes, so-called seeds, which can be obtained from databases, literature, or wet lab experiments, and then studies their interactions with each other and other biomolecules and biological interaction networks, most commonly protein-protein interactions. Based on the observation that disease-associated genes are not randomly scattered throughout these interaction networks, algorithms then try to extract a disease-associated subnetwork which aims to capture the mechanism. These subnetworks or disease modules then typically also include proteins which weren't part of the initial seed set, which can serve as novel therapeutic targets. This can be leveraged to identify compounds by selecting drugs that are known to target one or maybe even more nodes in the module, which also works great in combination with drug repurposing, which can be considerably cheaper and faster than developing new drugs from scratch. All right, while the overall goal of disease module inference is clear, there unfortunately isn't a general mathematical definition or guide on how this can be achieved best. And as a result, a bunch of algorithms have emerged that are based on different assumptions and use different modeling approaches. A first neighbors approach, for example, where calling it an algorithm might arguably be an exaggeration, simply expands the seed nodes by including all proteins which directly interact with at least one of the seed nodes. Diamond also expands the initial seed set, but in an iterative fashion, adding one node at a time, the node that has the most significant number of interactions with the seed sets, considering its overall node degree. Domino, on the other hand, works a little differently. It first partitions the networks into non-overlapping clusters, and then returns and further refines those clusters that have a higher than expected number of seeds. Robust has yet again a different goal, which is to connect the seeds into one single shared components by including intermediate network nodes using diverse price collecting Steiner trees. And then there's also its research bias-aware implementation, which works exactly like Robust, but penalizes the inclusion of heavily overstudied genes by considering the number of times a protein was used in protein-protein interaction detection experiments. Then there are also network or heat propagation methods, like, for example, random walk with restart, which expands the seed sets in all directions using a simulated random walk with restart. And the particular implementation we will have a look at later continues this expansion until all seed nodes are part of a single connected component. So it not only has the goal to expand the seeds, but also to connect them. And as you can see, these methods are based on quite different ideas, like connecting the seed nodes, expanding from them, or network clustering. And unfortunately, we don't really know which approach works best, because evaluating disease modules is incredibly challenging, mainly because, as for many problems in biology, a full ground truth is usually not available. Because of this, it can make sense to try multiple of these algorithms for your specific problems, which can be tedious because they require different input formats and software dependencies. And even if you go through the effort to setting up multiple of these algorithms, you still somehow need to decide which one is the most reliable. And that's why we developed the Nextflow pipeline that runs disease module inference algorithms and thoroughly evaluates the results. Some of you might also be familiar with the NF Core framework, which provides a collection of community-curated Nextflow pipelines. And our pipeline here, NF-core disease module discovery, is actually the first one listed there that has anything to do with biological networks. So NetBio, let's go develop some of the pipelines, because as a Nextflow pipeline, the whole workflow can be started using a single command line command. And software dependencies are then automatically deployed using either Docker or Singularity. You also only need to provide two input types, which are the aforementioned seed set and an interaction network. The seed set has to be user provided, but for the network, you can either provide your own or select from a bunch of choices available through the pipeline interface, which I will come back to later. For both of those inputs, you can also only provide a single file or multiple, which makes it possible to conduct a broad analysis covering multiple diseases or networks. All right, let's have a look at the pipeline. We will first follow the screen line, which resembles the core workflow of the pipeline and starts with running the 6 disease module inference algorithms introduced earlier, the results of which are then individually evaluated. A typical approach to evaluate the biological relevance of disease modules is to check for overlaps with known, maybe even disease-associated biological pathways. For this purpose, we deploy gProfiler to perform overrepresentation analysis and report enriched gene sets. Related to this is the tool Digest, which also relies on prior pathway knowledge and was specifically developed to evaluate the quality of disease modules or gene sets in general. Digest is based on the assumption that the genes in a module should be functionally coherent, which means they should appear in similar pathways, which is evaluated using empirical p-values. We further report topology measures of the module, which include the number of seeds, the number of nodes and edges, as well as the diameter and number of connected components. And we also compute pairwise overlaps of the node sets of the modules to compare disease modules obtained via different methods, networks, or seed sets. In addition, we also include the network medicine tool DrugStone, which we use for 2 different purposes. The first one is to generate drug repurposing hypotheses using network-based drug prioritization algorithms. And the second one is its web export feature, where we generate one hyperlink for each disease module, with which it can be interactively explored and visualized directly through the DrugStone web interface. However, we also offer offline network visualizations. And we annotate the disease modules using supplementary biological information from Nextflow, including targeting drugs, the side effects, associated disorders, or the cellular components of proteins. In addition to this core workflow, we perform also some more computationally demanding input perturbation-based evaluation procedures, which can be efficiently parallelized using Nextflow. Specifically, we perform a leave one out analysis, where we move one seed node at a time from the initial seed set and then rerun the algorithms based on the modified input. This allows us to assess 2 things. First, ideally, the disease modules would not overly rely on a single gene. So we compare the original modules to the permuted modules and assess their robustness towards small input permutations. Second, the left of seed nodes are actually the closest we have in the pipeline to a real ground truth, since we know that they are relevant for the disease mechanism, and therefore the algorithm should be able to re-include them, which can then also serve as an estimate of the algorithm's ability to include additional disease-associated nodes. Prior research has also shown that some of these algorithms tend to heavily rely on the node degrees of the seed nodes in the input networks. And to detect this bias, we commute the input network multiple times using degree-preserving rewiring, so switching the edges but keeping the node degrees of the individual nodes. We then run the algorithms again based on these permuted input networks, and this time we want the modules to change, because if they don't, we know that they mainly rely on node degrees. In the end, we provide a summary report for the pipeline using MultiQC. MultiQC is a standard choice for many NF-core pipelines, and it offers inbuilt support for a ton of popular bioinformatics tools. Unfortunately, the tools in our pipeline aren't quite popular enough to have inbuilt MultiQC support, which is why we leverage its feature to include custom content to the maximum in order to provide a comprehensive HTML report, including the most important analysis results, as well as execution details and software versions. And that was basically an overview of all the features currently included in our pipeline. As mentioned before, you can either provide your own network, but you can also select from a range of included networks, which include networks from BioGrid, IID, HIPPY, Networks, and String. And for some of those networks, we also offer multiple variants based on different confidence levels. And we translated all those networks into different ID spaces to match the user input used for the seed files. And as you can see there, here, the networks differ quite substantially in size. So we offer both high confidence as well as extensive network options. We demonstrated our pipeline using these 10 networks in combination with 5 seed sets for 5 diseases obtained via DisGeNet, resulting in a total of 50 input combinations, which we analyzed using a single pipeline command. And these 5 diseases include Huntington's disease, ulcerative colitis, Crohn's disease, ALS, and the cancer type lung adenocarcinoma. And as you can see here, the number of disease-associated genes varies per disease, ranging from 40 to up to 280. Due to the limited amount of time, I will only present you 2 of the results obtained through this evaluation case, and the first one is module overlaps, and I think both of the results I'm presenting you will highlight some of the limitations of current approaches. And this slide shows you a heat map for each method included, visualizing the Jacquard similarity of modules obtained using different diseases and networks. And here we would assume that despite the fact that the networks are quite different in size, the disease modules should still be specific for a disease and therefore cluster in the heat map. And as you can see, this is indeed the case for the top row, including domino, robust, and robust bias-aware, but not really the case for the bottom row, which also tend to be the methods producing bigger modules, which is most likely the reason why they lose specificity. However, this comparison isn't entirely fair, because the seed nodes, which we include in the beginning, are of course already disease-specific, and they are part of the modules as well. Because of this, we also calculate the overlap excluding the seeds, focusing only on the added nodes. And like this, the disease modules do not cluster per disease type anymore. Which means that the added nodes are actually heavily impacted by network choice to a point where disease specificity is largely lost. The second result I want to talk about is the seed rediscovery, where we hide individual nodes and check if the algorithms can recover them. And as you can see in this chart, the most reliable way to recover most of the left out seeds nodes is just including all direct interactors of the remaining seeds, like the first neighbors approach does it. However, there's also a catch, because first neighbor modules tend to become very large, and it's of course way easier to re-include a node if you're adding a lot of nodes in general. That's why we also report a normalized rediscovery rate, which we divide by the number of module nodes in each module. And like this, the differences between methods are far less prominent, and actually diamond and random walk restart yield the highest median rediscovery rate. Let's also have a look at the rediscovery on the gene level. And this heat map shows the seed nodes used for Huntington's disease, and each cell resembles the number of times the seed gene was recovered using different networks. Since we use 10 networks in total, that's the highest achievable value, meaning that it was recovered every single time. The rows are sorted by row sum, and maybe you remember the Huntington example from the beginning, which causes Huntington's disease. Therefore, it would be very nice if the algorithms would be able to recover it. And indeed, Huntington is the second most frequently rediscovered seed node, which is a good thing. However, you can also see that some algorithms aren't able to rediscover it at all, and others only with specific network combinations, which means that overall most methods struggle to recover this gene reliably, which is a problem that this gene is definitely at the center of the disease. Summing up, our pipeline provides easy access to multiple disease module discovery methods, and maybe even more importantly, to an extensive evaluation framework with which you can compare multiple disease module discovery methods. It's also modular by design and easy to expand, and we have a whole list of algorithms which we want to include in the future. I think the 2 results I showed also show that current approaches aren't without limitations, and that's why we also hope that this pipeline will serve as a platform to evaluate upcoming algorithms and networks to keep progress of the field in the future. With this, I want to acknowledge my co-developers, with whom we are collaborating through the Repo4U project, as well as the group I'm working with, which is DaisyBio, and many of them are also attending the ISMB, as well as the NF Core community for their current and future support in developing, maintaining, and hosting the pipeline. We are currently working on a preprint, which unfortunately isn't out yet, but the pipeline itself is already available. So if you're working with the Z's modules, feel free to check it out. And if you think something important is missing, text us or create a GitHub issue or anything like that. Yeah, as mentioned before, our group is attending the ISMB this year, also with a range of different topics and posters and talks. So if there's anything interesting for you, make sure you pay them a visit. And with this, I want to thank you for your attention, and I'm happy to answer your questions.
Hey, great talk, and it seems like a really helpful tool, so thanks for providing that community. So I'm wondering, some of the methods provide you just a set of genes, so the first neighbor, whereas like random walk of restart, where essentially you score for each of the genes like protein network. And I feel like maybe those two different types of classes of methods, they use different verification. Because when you collect a score for each of the genes, you can do some kind of distributable curve, whereas if you just get a set of genes, you can't do that. Do you have any words of wisdom when it comes to that?
I don't know if I would call it wisdom, but you're of course right that there's a difference between like continuous scores and binary features. Like currently, I think as you've noticed, we treat everything as binary, and if there is a score, we convert it to a binary feature basically based on a cutoff. But you're right. I think, yeah, precision recoil curves are, again, of course, difficult if you don't have a ground truth. But I think supporting something like this for methods that produce continuous scores is a really good idea, because it would also allow you to do like hyperparameter training, right? Finding that cutoff. So I would need to think about for how many methods that would actually make sense, but it's definitely a good idea. Thank you very much.
I just want to say that I absolutely love this idea and the work. It's really great.
Thank you.
So just a quick question, like you said that some of the results, some of the modules overlap with disease, but depends, the results depend on the input network that you use. Do you have an idea of how to solve that problem? Maybe combining networks, or how do you see solving that issue? The results depend on the network.
That's a good question, mainly also because I think if you have publications about these topics, like which seed nodes are used and which method is used, that's usually like highly explained and discussed, but the network's choice often isn't. I think, unfortunately, just from the other evaluation results, that will probably will not be a one-fits-all solution, because also different methods seem to perform better with smaller or bigger networks. Domino, for example, was demonstrated like using a small network, and when you use it with a really big one, it really gets unstable. But on the other hand, I would generally say bigger networks probably have more information, so use that if it's available, but it also depends on the algorithm.
How about tissue specificity, including tissue specificity and tissue-specific networks, maybe, which then would be more appropriate for the disease?
That's another excellent question or suggestion, actually. We are planning to provide a pre-filtering step where you provide a network, and then you can also provide a tissue which you're interested in, and then we would filter the PPI network based on protein expression in that specific tissue, which should then make it tissue specific. And that's, yeah, definitely a very important point, because protein reactions are tissue specific.
Great work, really.
Thank you.
So we will take one more question, and then we will take other questions offline.
Okay, Lars Jensen, one of the people behind Spring. Thanks for including it.
Welcome.
One quick question here. It's great work, but one of the challenges with Spring, unlike many of the networks, is that it's fundamentally a weak network, right? That's why you have 4 versions actually.
Yeah.
Any thoughts on how to deal with that? Because in our experience, when trying to do this kind of work on top of the networks, what works really well are things like random walk with restart, where you take into account the edge weights as the probabilities when you're doing your walks, instead of discretizing it into there is an edge or there's no edge.
I never actually thought about using the confidence levels as like weights for the networks, which I think is a great idea. I guess it would work with random walk with restart, but robust should also work, and maybe others. The only thing I would be a little bit worried about is, again, this research bias, because I would assume that you have the high weights then again for highly well-studied proteins, and then you would be more prone to including those, but they will most likely not provide you that much prior knowledge because they also already heavily studied. But generally, something like this would definitely be more the elegant solution than just providing different versions, because you can also not go infinitely deep there regarding resolution. So yeah, that's something we should definitely think about. Thank you.
Great. Happy to talk over lunch if you want.
Yeah, you're welcome. Thank you.
Thank you. And thank you for all the enthusiasm. So we will take the other questions offline, because we need to move on to the next talk. Thank you, Johannes. So.